All right, so we're going to do the review for Unit 6 test. So question 1 says, write 7th root of 5 to the 8th power using rational exponents. So the idea here is that our exponent, our 8, stays as the exponent. And it's going to be the numerator. Because remember, our rational exponent, we're going to write a fraction. So we're going to put this number on top. The 7 is going to become our denominator. So right now this is the index, and we're going to make that the denominator of our fraction. 5 is the base, this just stays as the base. So we say 5 to the 8/7. And that's it. That's the entire question. So it's just rewriting from our radical form to our rational form. So for question 2, it says solve the equations for x. So this is all the exponent rules from the beginning of the section. X to the 9th divided by x squared. So remember, when you're dividing, the rule is to subtract the exponents. So since 9 minus 2 is 7, we get x to the 7th equals 2187. So that's a pretty big number, is x to the 7th, because we have to think what number raised to the 7th power would be 2187. So we could do guess and check. It's going to be a little bit easier to solve it, though. And to solve it, remember, we can undo it by taking the 7th root of both sides. Now this is something that you're going to want to throw into a calculator. So I'm going to bring up Desmos, and we're going to do the 7th root of 2187. So let's see. We can't do a square root. Let me move my little camera controls over here. I can. There we go. So what I want to do is take the 7th root. It's hiding in the functions menu. We got to hit miscellaneous, and we're going to hit that little nth root. Get rid of that one. And we're at the 7th root of 2187. So it ends up being 3, which I guess we could have guessed and checked that one. We know it's not going to be 2 because it's not even, so we try and eat an odd number no matter what. But our calculator gave us x equals 3. And again, if we tried, 3 to the 7th is going to equal, well, let's put that over here. 3 to the 7th is going to equal 2187, and that's why the answer is 3. For the second one, we've got a power to a power. So the rule for a power to a power is that we have to multiply the exponents. So we've got 2 powers, so x times 4 is just going to be 4x. So kind of weird. We just got 5 to the 4x right now equals 125. And the idea is, before we can find out what we're going to get, we need to make sure that the bases are the same. So right now this one's a 5, so I need to turn this one into a 5 also. So this side is going to stay the same. We're going to leave that as 5 to the 4x. But this has to become a 5 to something. So again, we might have to do some guess and check, but we know that 5, so the first power is 5. 5 times 5 is 25. 5 times 5 times 5, 25 times 5 is 125. So since we had to multiply 3 5s together, we get 5 to the 3rd power. Since the bases are now the same, they cancel each other out. So we get 4x equals 3. Divide both sides by 4. And so we end up at 3/4, or if you want, you could say 0.75. Let me circle this 3 over here. Box of 3. All right. Last one over here, part C. So when we're dividing, we end up subtracting. When we multiply, we're actually going to end up adding the exponents together. So we're going to get x plus 1, 7 to the x plus 1. It's not a good one. Plus 6x plus 2 is equal to 7 to the 11th power. And just like we did over here in this one, since the bases are the same, the two 7s are the same, they can cancel out. So we get x plus 1 plus 6x plus 2 equals 11. And now we get to solve this one like it's an equation from Unit 1. So we're going to combine all the like terms. So everything that's on the same side of the equal sign can combine here. X and 6x is 7x. 1 and 2 is 3. Nothing can combine on this side, that just stays as 11. We can subtract 3 from both sides. Again, we're trying to get the x's by themselves. So 7x equals 8. And then divide both sides by 7. So x equals 8/7. And that one we're all set. So we can see with some of these ones, the first one we could have done with guess and check, but the other two we can't. The other two are fractions or decimals, and it's going to be really difficult to try and guess and check those. So you're going to have to actually use the exponent rules to figure those out. There's no really quick shortcut with guess and check like we could do on the first one. So that's it for number 2. Number 3, we've got a sequence. So we just have to write the two forms. So the explicit form is the one where we could plug a number in and get the answer. So the explicit form is going to be the one that goes, oops, I want to use the same colors that they do. Oh, so yeah, A sub n. A sub n equals, and we're going to have A sub 1 r to the n minus 1 power. I'm going to put that in parentheses too. I like all the parentheses. You don't need all the parentheses if you don't want them. But we said A sub n always stays the same. A sub 1 is the first number in the sequence, so A sub 1 is 64. And then r is what we're multiplying by every time. So if I'm not sure, I can just pick two numbers. We can pick the first two or the last two are nice and easy. I'm just going to pick the first two because they're whole numbers, and we can divide them. So r is going to be the second divided by the first. First one is not 16, it is 64. Usually in class we'll do the last two just because those numbers will be smaller. In this case it might be a little bit more convenient to pick these ones. Even the middle ones are a little bit more convenient because then we don't have to reduce to 1 over 8. But we're multiplying by 1/8, or we're dividing by 8 every time, because 64 divided by 8 is 8, 8 divided by 8 is 1, 1 divided by 8 is 0.125. N minus 1 never changes, that stays as n minus 1. And that's it, it just asks us to write the sequence, so the sequence is over. For the recursive, this is one that's got the two parts. So the first part tells us that A sub n equals, and we're going to do r. And now we're not going to do a little n minus 1. It's not going to be an exponent. It's just going to be times n minus 1. Oops, sorry. Mess that up. We don't want it up there. We want A sub n minus 1 because we want to do the previous term. There we go. A sub n equals r times A sub n minus 1. And then we also have A sub 1 equals whatever number we have for A sub 1. So I color coded it so the blue number is always the same. So whatever number we want for A sub 1, which again is just going to be 64, we can just say A sub 1 is 64 because we need to say where the sequence starts. So even though up there we know we're multiplying by 1/8, we need to know where we're starting to get to all the numbers in the sequence. So this is the start, and then this is kind of the formula. A sub n is going to be, we're always going to multiply by 1/8. And you're always just going to multiply by the previous term, A sub n minus 1. And so that's going to be the form. And you want both parts because the top part is the instructions and the bottom part is where to start. So you need both parts for that one. The explicit you can just plug right in for n. It's just got one part to it. All right, next one we have to find out if this is a geometric sequence. So since we're looking for a geometric sequence, we're automatically looking for multiply. So I need to make sure that I can multiply by the same number every time. So if I go from 1 to 2, that's a times 2. 2 to 4 is also times 2. 4 to 8 is also times 2. So I want to check them all out. They all worked out. And it worked out because we could multiply by 2 every time. And that's the whole rule for the geometric sequence. So that's it with that one. I remember the arithmetic is the one where you add every time, but in this case we're multiplying because we're looking for a geometric from this unit. Use the exponential to answer the following questions. So again, this is pretty early on in the chapter, but what's the y-intercept? Well, the y-intercept is where we cross the y-axis. I'll do that in blue because it's going to be the same number as a. So 0, 2 is the y-intercept. What's the equation for the asymptote? Well, the asymptote is where we get close to but never touch, and it looks like we're kind of stopping right at this line, right at the x-axis, and that's the line y equals 0. So remember, we're going to get really close to y equals 0, but we're never going to touch y equals 0. So in section 5, remember we can move our graphs up or down, so that'll change our asymptote. This one's nice, it's just right on the x-axis. What's the domain? Domain is always the same for all exponentials. The domain is negative infinity to infinity, all the way to the left, and then all the way to the right. So this one will keep going off to the up and to the right. This one will keep going all the way to the left. Range is going to deal with the asymptote. So we're going to start at 0, because that's where the asymptote is, and our function's going up, so we're going to go all the way up to infinity. If we were flip-flopped, then we would say like negative infinity to 0. That's if we had something that was going in the opposite direction, if it was flipped. If it's falling down, you still go 0 to infinity, because the lowest is still 0 and the highest is still infinity. So that's just some of the characteristics of the graph. All right, for 6, we get into a really big question, because this one says Troy's got data points for a function, but he's unsure whether it's linear or exponential. So to write the model formula and fill in the table values for each option. So this is a big one, because we have to compare everything that we did previously in the first semester with the linear functions with the stuff we just learned this quarter with the exponentials. So we have to remember that for the linear, the idea is we have to add, and for the exponential, the idea is we have to multiply. So this is going to be a little bit tough because we don't have the numbers right next to each other. So we might have to do a little bit of guess and check. We might have to think a little bit to find out how we can get to 45 in 2 steps. So if I add, I got to think, well, there's 40 difference between them, and there's 2 between them. So 40 divided by 2 should be 20. So if I add 20 every time, it will work out. If we want, this is pretty cool. You can actually use the slope equation, which I'll do right here, really quick down here. y2 minus y1 over x2 minus x1 to solve for it. So 45 minus 5 over 3 minus 1 is 40 over 2, which is 20. And that does tell us that we have to add 20 every time. So to fill out the rest of the chart, we'll add another 20. If we're going backwards, we don't add, we subtract. So negative 15. All right, well, I know how much I'm adding every time. I know where I'm starting. And I know the function for linears is our friend y equals mx plus b. So our function is going to be y equals m's the slope. M is how much we added every time. X doesn't change. Remember, in this formula, b isn't how much you do every time. B is the y-intercept. B is what you start at. So minus 15. And so that's our linear function. So now we got to do it for the exponential. So the exponential is a little bit harder because we have to decide, all right, we have to multiply every time. All right, well, let's see. 5 times 2 would be 10. 10 times 2 would be 20, so it's not 2. 5 times 3 is 15. 15 times 3 is 45, so that actually does work out. So we could do it with guess and check if we wanted to be fancy. There is a formula that we didn't use in class, but we could kind of mirror like what we're doing. 45 divided by 5, and the formula is a little weird because it's going to be the 3 minus 1th root. So you're probably not going to use this formula. Probably just best to look at it and try some numbers out to try and divide or multiply. But we can figure it out if we want to do the square root of 9. We can get 3 that way. But again, we did not do that one in class. That's a little bit of an advanced technique. But if you want to try it out, you can. Again, we're not going to do anything crazy. By most the square root, or even just if the two numbers are next to each other, just find out what you get when you divide them. But anyway, 45 times 3 is 135, so that goes there. We have to go backwards, so we have to divide by 3, and we get the fraction 5/3. That's okay, fractions are okay. So for the exponential, if we remember, our function is y equals a times b to the x power. So we'll just fill in. Y doesn't change. A is the y-intercept. So 5/3 this time. B is how much we multiply by. And then x stays as x. So remember, we don't need to multiply the 5/3 times the 3. We're just done right there. So that's it. We're just looking for the equations. Just like for the linear one, we don't subtract the 20 and the 15. It's a little bit more obvious there because the x is between them. But we don't multiply the 5 and the 5/3. Again, that's why I like the parentheses, because it kind of puts a stop to it and says, hold up, don't actually multiply, where you might see it with a time sign sometimes. So that's that question. For 7, we have our investment of $2,500 is placed into account that pays 3.5% interest compounded quarterly. How much money will be in the account after 25 years? We need to know the interest equation for this. So our interest equation tells us that our amount is equal to our principal. And then we're going to multiply by 1 plus the rate over n to the n times t power. So we're just going to fill in. And remember, this equation is just y equals a times b to the x. We just kind of switch all the things around to suit our needs. We're trying to find out how much money. So how much money is a? So that means that we don't know a, so we'll just leave a as a. P is the principal. P is how much you start with. So it's going to be $2,500. 1 plus R is the interest rate. That's 3.5. Or we have to do 3.5 divided by 100. So 0.035. N, we have to find the keyword for N. So the keyword in this one is going to be quarterly. Quarterly tells us that N is 4 because there's 4 quarters in a year. And then T is the time, so they tell us the time right here is 25 years. All right, and at this point, we can just throw this right into a calculator. So again, since I have Desmos up, I'm going to throw it into Desmos. All right, so we don't need that one anymore. I don't want to put the A equals in here, so we'll just start with 2,500. 1 plus 0.035 over 4 to the, and again, Desmos, you need to do the parentheses. If you have the handheld calculator, you don't need the parentheses, but it's not going to let you type 4 times 25 as an exponent if you don't have the parentheses. You're going to get the wrong answer, even if you set it up right. And we get our result. So we get 5974.41. $5,974.41. And that's $5,974.41. It's totally fine to round that to the nearest dollar, so you could write 59.74 if you want, because again, we're dealing with how much money after 25 years. 41 cents probably not going to make too much difference over 25 years. Part B asks how much money was made after 25 years. Well, to find out how much money we made, we know how much we have at the end. And we know how much we had at the start. So if we subtract those, that's going to give us our profit. Because sometimes that's more important than the final number, is finding out how much profit we actually make. So 5974.41 minus 2,500 is going to be, well, we get the 41. We get the 74. 9 minus 5 is 4. 5 minus 2 is 3. So $3,474.41. So we'll just subtract those. Again, you can throw that in a calculator if you want. This one turned out to be nice. We could do that without a calculator. All right. And then last question. So there are 2 bacteria colonies that are being studied. So colony A, initial population of 20, rate of growth is 34%. So that one's going to go up. I'm trying to think how I'm mirrored in the picture. Colony B, initial population of 1,000, daily rate of decline is 30%. So this one is going down. I think that's the right way to do it from the picture. Part A says how many bacteria will be in each colony after 2 weeks. So it looks like we're setting up a growth and decay equations for each of these. So we'll start with colony A. The nice thing is for both of these, we're just going to use the same formula. Y equals A times B to the X. So that's going to be the equation that we're going to use. And we know we want that because we have a percentage growth and decline. So we know we need the exponential function. So we get y equals A is always the initial population, so 20. B, since we're doing growth, we have to turn growth into 1 plus R. And then X is going to be the time in this case. We'll turn that into a T. So I'm going to substitute twice just to show where all the variables go the first time. I don't think we'll do that on the other side, but for this one we want to. So we get 20, 1 plus, so again, 34% is 34 over 100, or 0.34, so 1 plus 0.34. And then T. Well, on T, it says 2 weeks. So we got to be careful. We've got 2 weeks, and this is a daily rate of growth. So we have to make sure our units match up. So in this case, 2 weeks is going to be 14 days. So remember, 7 plus 7 is 14 days. All right, well, we've got our formula, so we can just throw this right into Desmos again. So let's go ahead and do that. 21 plus 0.34. So we'll get rid of this one. So 20, 1 plus 0.34, that's a comma, 14th power, so 120364, but we're talking about bacteria, so we probably want to go to the nearest whole number. So either 1204 if you want to round up, 1203 if you want to say, well, we don't get the last bacteria yet. Either one is going to be okay. It's up to interpretation. I'm going to say 1204, I'm just going to round it, but either one would be okay. Wait, was that 1204? Yeah, okay. All right, so that's what we've got for colony A. For colony B, we kind of set up the same thing. Let's do it exactly as it looks over here. So y equals our initial population is 1,000. But since we're doing a decline, since we're doing a decay, we're going to do 1 minus r instead of 1 plus r. I'll just keep it the same. We'll put the t there. And the next line we'll replace. So we get 1,000. 1 minus, so 30%, 30 over 100 is 0.30, or 0.3 if you don't want to keep the other 0. And time is still the same. We're still doing 2 weeks, so we're still going to go to the 14th power. So 1,000. I like this, so why don't we just copy and we'll just paste that same form. 1,000, 1 minus, instead of 0.34, 0.30. 6.78. So we'll just round that to only 7 bacteria. So most of our bacteria are dead over here. So if this is a disease, then maybe whatever we did with colony B is good because we killed a lot of the disease already. So that's pretty good. For part B, it says, when will the 2 colonies have the same amount of bacteria to the nearest day? Well, we know that colony A started at 20, got up to 1204. Colony B started at 1,000 and went down to 7. So it's got to be between 1 and 14. We could do guess and check, or if we want, remember, we can use our solving techniques from our systems of equations. This is why I kind of kept both of those there. I'm going to turn that into y equals. And instead of a 14 up here, since I don't know what time I'm going to have, I'm going to pick x. So you can see our nice exponential growth. Over here, same deal. We'll turn that into y equals. Change that into an x, and now I don't even see a graph. But remember, that's because we're starting at 1,000, so I actually have to zoom out a lot. So I can zoom out. I can see, okay, there's the decay. Now I can see it clearly going down. And just like we did with the systems of equations, we got to find where they meet. So they're going to meet right here. So after 6.025 days, they both have 117 bacteria. Well, this question only asks for how many days. So all I need to do is say it's going to be 6 days. So when will they have the same amount of bacteria? After 6 days. And then to solve that again, we just graphed, and then we found the intersection. Find intersection. We could have done it with guess and check, because again, there's not too many numbers. It will be annoying. So if you do want to do guess and check, it would be best to start in the middle and then just kind of keep halving every time. So do a Newton's method approximation. to try it so that you don't have to guess all the numbers starting from 1 to 14. Because if you try 7 and you see that colony A is too big and colony B is too small, then you know it's between 1 and 7. And so that really cuts down the amount of guess and check work you'd have to do. All right, well, that's everything on the review guide. So I guess we'll be all set.